So, as you might have seen in the visualization, whenever you add a new node, you always add it as red. You almost always have your root as black. So you want your root always to be as black, and you can. These are not properties, but well, you can view them as properties, but they are how the trees actually function. So, uh, well, if you go through these two animations, you should hopefully understand how things are. Uh, the red black tree implementation is you I mean is basically what is used for. You can use it to implement maps, for example, and this is the way that Java, for example, implements the tree map data structure. uh, you can take a look. I mean, the whole implementation is described in Corman, and Corman is the algorithms and data structures book that you absolutely completely need to own. I think that this is probably the most important book I can think of in computing science in general. I'm not. You don't need to buy it. It's thankfully available through the library as yeah, through this link basically, and it's available online. So you don't need to buy it. You can check it, and I would highly suggest. I mean, it has nothing to do with the operating systems course, but I think that it's important. I know that the efficient algorithms course uses it, but I'm not sure if everybody takes the efficient algorithms course. So the Linux red black tree implementation is in /lib/rb3.c, and you can see the implementation actually over here, and they have a pretty good documentation of how the red black tree is implemented, so you can actually read a bit more even on the implementation. uh, the red black tree implemented in Linux does not provide with search and insert routines, and they realized that well, both search and insert are typically very optimized for your application, so they basically gave you a choice to re-implement them, use the implementation that you deem the most suitable for your application. So they are not implemented, and you're expected to define your own. And this way, they kind of make sure that you will have the optimizations that you need uh, in your system. With this, I will not talk anymore about red black trees, but I would like to note that I know that a few people have been trying to use the hash tables, the .c/.h, in the kernel that they found, but people have not been happy, as I've heard. It's a ready-made implementation of hash tables in the kernel. There's actually another implementation of hash tables that you might want to look at. It's called R hash tables. These are actually two tutorials on how to use R hash tables in the kernel, and I think they might remove some of the issues that some of you have been having with the hash tables implementation. And yeah, this might be a good replacement for your project, so take a look at that. So let's talk a bit more about Linux kernel modules. And before talking about Linux kernel modules, let us talk about devices. And devices are classified into one of three types. The first one is what is called block devices, the second one is character devices, and the third one are network devices. Block devices are basically addressable in chunks, so you basically read the block, and they generally support seeking, for example. So this is something that you would use, for example, for a CD-ROM, if you're building a device driver for a CD-ROM. The second type is what is called character device, or CDEVs, and these provide access to to data using only a stream, and that's generally of bytes, a stream of bytes, of characters or bytes. And you can find an implementation of MIS devices. They're character devices also, that are sort of miscellaneous devices, not just appointed to something special. And then there are network devices, and they basically break the Unix's philosophy of everything is a file, and they are are implemented rather to be suitable for network streams. So, and there you use socket APIs slash socket programming, and there, yeah, they're used. You use socket APIs, and yeah, if you're familiar with socket programming, then this should be quite simple to use actually. There are virtual devices, and some of them are very common, like slash dev slash random slash dev slash null slash dev slash urandom slash dev slash zero slash dev slash full slash dev slash mem. I mean, these are all virtual devices. They do not map to a real device, a hardware device. Although most of your devices would actually map to a real hardware device, but you can still implement many of them into basically virtual devices. So in, many people are actually choose. I mean, well, you're in your Linux in your LKM implementation for the project, you're going. Most people are going for some kind of virtual devices to basically interface with the LKM. That brings us to modules. And modules are actually a way to support the dynamic insertion and removal of code into the kernel. And they enable you to do that at runtime. Most of the modules you would actually start developing them, start writing them more close to the user space, and then basically recompile them or compile them, attach them to the kernel, and then they would run as if they are part of the kernel. And the reason that modules are very useful is that you typically want to, for example, when you're testing a device driver, if you just made, I mean, if you just got a new GPU, for example, and you want to start writing a device driver for this GPU, writing the device driver directly into the Linux kernel would probably result in a few errors that would result in the kernel not even compiling, or worse, that the kernel, you will not be able to start the machine at all. So one fast way to do that is that you have your kernel already running, you start trying to load modules into the kernel, and then if they fail, then you will not have the full system, not the full kernel not being able to compile, but rather get a more directed error towards what is exactly the point, the problem. And that also speeds up the development cycle because you do not need to recompile the kernel every time you change a single line of code. It allows systems to have also a minimal base kernel image to some extent, so your base kernel will not include the modules. That being said, you can actually run the modules in the kernel. So you can, after developing the modules in kernel space, sorry, in user space, you typically port them into the kernel space, and then they become part of the kernel. You patch them, and they become part of the kernel. Module development is more like writing a new application, at least in the sense that you have a well-defined entry point and well-defined exit point. And well, these live in their own files. Let's look at the hello world kernel code. And first you need to include init.h, you need to include module.h, and you need to include kernel.h. And these are the basic three includes that you would need. Then the very simplest kernel module would look like this. You will have an entry initialization point, and you will have an exit point. So static int hello int is hello init is your initialization to basically load the kernel to the kernel module, and you have an exit function that is basically called here hello exit, that takes void and that basically exits. And you initialize your module by basically saying that module underscore init, which is one of the it is a macro that tells the kernel where to look for the entry point to your LKM, and you have module exit, which basically points to the kernel to what it should run when exiting the LKM. You also have, if you macros that you need to define. One of them is module license, and that basically that is actually useful because it tells the kernel and it what kind of license this code is running with, and the kernel can actually so some kernel developers, for example, would not uh, allow their kernel code to deal with modules that do not have a GPL license, for example, or some open license, because well they believe in open source. But it also allows, for example, when if you have been developing a device driver with a module license that belongs to, let's say, Intel, for example, and me as a kernel developer looking at the current open issues with the kernel, current things that are throwing errors, and I find something that has a license from Intel, I would pretty much not touch it because, well, this is probably something Intel specific and they will fix it. Okay, so some people use it to basically prioritize also what work they are going to patch in the kernel. And you have a macro to basically say who's the author of this module, and a macro to basically add a description to your module. The kernel will invoke hello init when the module is loaded, and the call to module init is not actually a function call, it's a macro, as I said, that will load this initialization function. All init functions must have the form of int my init and take void. And within the init function, you can call other functions basically. Init functions are typically not directly invoked by the external code, so you should not expose them to the external code, so you can mark them as static. If you want to expose other things to, if you want to expose some things to the external code, then it's not your init function basically. You have an exit function which acts as the kernel invokes basically when the module is being removed from memory. It is supposed to basically clean up whatever your module has been doing. The exit function frees resources, shuts down and resets hardware, because you might be writing this module to control, for example, a USB stick or something, and perform all cleanups that are needed. So it basically undoes whatever you have been doing in the kernel module. I talked a bit about the module license, and the module license allows the kernel developers to see, I mean, it allows the kernel to basically raise a tainted flag. So this is dirty. This is not ours, sort of. There is a really nice walkthrough on how to build kernel modules, and this is actually quite recent. I know some people have been complaining about the mismatch between many of the tutorials online and the kernel version. Yes, this happens, and yes, I mean, I try my best to actually get a tutorial that is up to date, but I mean, the kernel changes much faster than the tutorials do, and that's why actually in assignment 1 I specifically said I do not care what kernel version you're using. I think that was highlighted in the text. I really did not care what kernel version you're using, because yeah, I mean, I know that everyone has learned a lot, hopefully, by basically going through the different files and understanding how does the syscall architectures change, and how to change them and so on. But I mean, if you had just picked an older kernel version, I would be fine with it, because the tutorials are just lagging, and there's nothing I can do to change that. And myself, I mean the Raspberry Pi 3 came out after I actually had started implementing started preparing for the course, and I had one of two choices basically: either to give you the Raspberry Pi 2s, order these ones, or get the Raspberry Pi 3s and run the risk that, well, some things will mismatch. But yeah, then I don't think that the mismatch was horrible. I think there is a learning curve. I think this is, I mean, assignments are not supposed to be basically me giving you every single piece of the information, but I believe they're for you to basically search and discover how to solve the problem yourself, because this is what you're going to do in a few months slash years, depending on what year you're in. And that's why I actually also encouraged you to start asking on Stack Overflow. uh, when I got approached by some of you, for example, on not being able to pass a struct, I basically got them an example from an already implemented uh, Linux kernel module, and sorry, Linux system call, and you will not imagine how many solutions I have gotten for the syscall assignment. I can actually, I think it might be of value at some point in time if you guys basically sit down together, or probably not all of you, but compare your designs. I think some of you have already done that, and I'm fine with this. But it would be actually cool if you start looking at how many different ways, how many different files have people changed. And some people actually followed some of the tutorials that I put pretty closely, and they arrived to a solution, but they basically needed to change one extra file, which I missed. So yeah, I'm just saying that this tutorial will help you to write the Linux kernel modules. This was written 2016, so pretty recent, but there is a kernel version that came after that. So take it with a grain of salt. And if something is not working, you can always go and ask over Stack Overflow, or just come ping me, or ping Strick, or ping Jan Eric. Okay, so let me continue. I'm just trying to get the. Yep. For compiling in and out of kernel, so I actually said that you can compile things out of the kernel, so that you have them at the user space, compile them, test them, run them, and then after testing, you basically redo this into several iterations. But you can also compile them in the kernel, and this is actually quite common. So once you have tested your modules, you would actually port them inside the kernel. You will apply for a patch, and after applying for a patch, you will get, well, if it's granted, then it will be upstream. And there are more than 10,000 kernel modules in the Linux kernel code, so there are a lot of them. And one really easy way to actually try to find your kernel, example implementations of Linux kernel modules, is to search the Linux kernel tree for basically the header file for including modules, and that's basically linuxmodule.h. So if you do that, you'll find a few thousand of them. So you can pass parameters to your Linux kernel module, to your loadable kernel module, and that can be done by basically using the module param macro, and it takes three values: name, type, and permission. Name will, in this case, will be the parameter, the name of both the parameter exposed to the user and the variable holding the parameter inside your module. So this can actually be a user exposed parameter that you can talk to. The type argument holds the parameter's data type, and it can be one of the following: byte short, u short, unsigned short, basically integer, unsigned int, long, u long, sharp, bool, and or inv bool. And well, these are roughly the normal C types. The permission argument specifies the permission of the corresponding file in sysfs, and we'll talk about sysfs later. Basically, the way that the drivers when you implement an LKM, loadable kernel module, there are multiple ways to allow the user to communicate with the LKM, and one of them is just through the sysfs. We'll talk about that later. But to have the permissions, you can have, I mean, the parameter in your module param macro would allow you to basically set some capabilities basically to your to your to your variable, or to the corresponding file in the sysfs basically. And these use the usual octal format, for example 0644, which would be basically owner can read and write, group can read, and everyone else can read. You can pass a 0 here to disable SSFS entry altogether, so there will not be a file produced to sysfs. Of course, you must declare the variable first before using it in the macro, so you must have it declared. So let's look at one example here for basically defining a value and a module param. And this would basically, suppose you have a new variable that you want to call allow live bait. So you define the variable first, and you basically then pass it to the module param. And in this case, you basically say that it will be a boolean type. You have, although you have it here defined with 1, but you say it's a boolean type, and you pass in the permissions. You can possibly also have internal variable name different than the external variable name, and you will in this case use module param named, and named will basically add an internal and will differentiate between an internal variable name and an external parameter. So if you want to pass string parameter, you basically pass it that way, either using char pointer to name, and then you basically pass name, charp, and 0. That basically means disable sysfs files. Or you can use module param string, and then you have name, string, len, permissions. And again, this is basically to differentiate between the internal variable and the external naming. And the convention is that you always have the external outside as the first parameter, and internal as the second parameter. So this will be your internal variable name. You can pass in comma separated lists, but by using module param array, which takes a name, type, num, and permissions. The new argument num is basically a pointer to an integer in which the kernel stores the number of entries stored into the array. So you pass to the kernel how many parameters are in the array that you're passing using num. It's a pointer to the integer, so you're not passing the actual integer. And the array pointed to by name must be statically allocated. It cannot be dynamic. You can also use module param array named again to basically have the extra differentiation between internal and external array types. This is an example, for example. So you can have static int fish, and this is your array, and then you basically have the number over here, and you pass the number as a parameter over here. So when the modules are loaded, they are dynamically linked into the kernel, basically, and dynamically linked binaries can call only into external functions explicitly exported for use. So you basically need to export these explicitly using export symbol and export simple GPL. And here's an example. So suppose that you want to basically export this function, which is called get pirate bird color. Okay, so you want to expose get pirate bird color. You will define it, and then you will export symbol get pirate build bird color.